Hi everyone. Thank you for organizing this workshop and giving me the opportunity to talk here. In this talk, I will present vector boson and jets measurements from CMS on behalf of the CMS collaboration. This is just a brief outline of what I'm going to tell you about today. So this overview includes studies of several results of vector boson production in association with jets. Let me first give a brief motivation about why we study the V plus jet measurement at CMS. The reason is the W plus jets and Z plus jets that are decaying to the leptonic final states are among the cleanest final states that we have experimentally. The production of vector bosons in association with jets in proton-proton collisions provide an important test of the standard model. This measurement allows to test perturbative QCD in a stringent way. It is also used to check Monte Carlo simulation and stands as one of the favored processes to tune this simulation. These processes are particularly interesting because they allow precision QCD tests with multiple renormalization or factorization scales set by the vector boson mass and by the associated light or heavy flavor jet transverse momentum. The clean signature and large production rate for this process provides an opportunity to accurately constrain the parton distribution functions and probe the strong coupling alphas. It allows to test non-perturbative QCD, and the production of massive vector bosons with jets is an important background to a number of standard model processes, such as single top TT bar production, vector boson fusion, Higgs boson production, as well as searches for physics beyond the standard model. So a good understanding of this process, this background is important to these surges and also measurements. Here we present measurements of cross sections of for production of Z boson in association with jets, where Z bosons decay into pairs of positively charged electrons or muons. So the measurement used data at 13 TeV corresponding to an integrated luminosity of 35.9 inverse femtobarn. So in this measurement, the cross sections have been measured as a function of inclusive jet multiplicities up to a total number of 8 jets. Here, Ricco level jet multiplicity results are shown for electron and muon channels separately. In these plots, the background is estimated from both simulation and data-driven methods. A ratio of simulation to data is also shown in the bottom frames with error bars that represent the total statistical uncertainties from the data and simulation samples. We can see that the jet multiplicity is modeled well until parton shower region greater 3 jets. So in this analysis, to remove the detector effect and estimate the particle level distributions in data, an unfolding method has been applied. So in the right plot, figure shows the measured cross-section as a function of inclusive jet multiplicity for combined channel. Results are compared with theoretical predictions, different theoretical predictions at next to leading order, and also with the Geneva predictions. So here we see no surprise in this plot as we expected. MedGraph at NLO is working well up to matrix element order, which is roughly 3 at leading order. Then in the parton shower dominated region, we see a bit of attention. So leading order is giving a good description within the uncertainties, and the Geneva generator predicts a much steeper spectrum than observed due to the lack of hard jets at matrix element level beyond the 2 jets. Systematic uncertainties used for the combination of the electron and muon channels are also summarized here in this table. Jet rapidity and PT distributions are measured up to 5 jets. In the first 2 plots here, the cross sections are given in terms of leading jet rapidity and also PT, while in the last plot, it's given in terms of the 5th jet rapidity and PT. So in the leading jet plots here, MedGraph 5, EMCA, NLO, is giving good description of the jet PT, leading order predictions up to 4 partons from MedGraph, EMC, NLO, and MLM matching scheme is predicting lower X section in most part of the PT spectrum. It's also important to note that X sections here normalize to the next to leading order cross sections. For the fifth jet case, we have a good description with both predictions. Here, we also did the measurements for several angular variables for Z-plot jet analysis. In terms of angular correlation between jets, cross sections are measured as a function of the difference in azimuthal angle delta phi. So for the angular correlation between the Z boson and jets, cross sections are also measured as a function of the difference and of the sum in rapidity. So here in the delta phi distribution, we see that in the low delta phi part, there is some tension here with Geneva prediction, as well as for the highest Y difference part. In slide number 7, the double differential cross sections are measured as a function of ZPT and also leading jet PT. So in the left plot, we show that with respect to the PTZ for different Z rapidity regions, and in the right one, we showed with respect to the jet PT for the different jet rapidity regions. The measured cross sections are corrected for the detector effects and compared with theoretical predictions at leading order and next to leading order, accuracy matched with the parton showering as implemented in the Monte Carlo generator. For PTZ distribution, we see that in the low PTZ part, Geneva is giving good descriptions as expected by the resumption. We also check the distribution of rapidity of leading jet in different Z rapidity regions as shown in the left plot, and also we look at the predictions to measurement ratio for the leading order MedGraph 5 EMC at NLO. So here we observe that leading order fails at high rapidity Z and low rapidity jet regions. So there is an undershoot of the data showing importance of next to leading order. So here we move to the W plus jet results. So we check the measurement of the differential cross sections for a W boson produced in association with jets in the muon decay channel. The measurement is based on the 13 TeV data corresponding to an integrated luminosity of 2.2 inverse pentabarn. In the left side, the left plot, you can see the detector level jet multiplicity distribution up to 6 jet. To check the background domination. In this analysis, we voted the events with B jets to suppress the TT bar contribution, especially in the high jet multiplicities. And also we use the data-driven estimation of QCD background. So in the right plot, the measured differential cross sections as functions of the exclusive jet multiplicities up to 6 jets are compared with the leading order and next to leading order predictions. The measured cross sections and the predictions are in a good agreement within the uncertainties. So in slide number 10, we also look at the measured cross sections for inclusive jet multiplicities up to 4 jets. We compare them with the different predictions as a function of the PT jet and also rapidity as just shown in the plot. So we just showed our results for the leading jet and for the fourth jet. So first 2 plots show the PT distributions, while the last 2 plots show the rapidity distributions. So the measured distributions cross sections as functions of the PT, jet PT and rapidity are better described by the next to leading order FX matching scheme prediction for all inclusive jet multiplicities and by the next to leading order calculation for at least 1 jet. In slide number 11, here you can see the recent V plus heavy flavor results from CMS. This measurement is important part of standard model physics program at the LHC because measurements of vector boson plus heavy flavor production can constrain the parton distribution functions of the proton. It also allows us to study the gluon splitting effect in BB bar. In this analysis, the process of associated production of jets, including B jets and Z boson decaying into lepton pairs, are measured using a data set corresponding to an integrated luminosity of 19.8 inverse Van Barn. Differential cross sections are measured for Z1B production as a function of Z boson PT and Z boson PT, and also as a function of leading B jet PT. We also, for also the 2B production, we show the differential extraction measurement as a function of delta RBB. So delta RBB is the distance between the directions of the 2B jets in the eta phi plane. So we also look at the difference prediction, and we compare the data with the predictions. So for the leading B jet PT spectrum, the ratio with data is reasonably flat below 80 GeV, whereas it presents a clear slope in the higher PT range. A similar behavior is also clear in the Z boson PT distribution below 130 GeV. In slide number 12, we also show the measurements of the differential cross sections of Z plus jet and gamma plus jet production and their ratio as a function of the boson transverse momentum. This work provides the first measurement of the ratio of the differential cross sections of Z plus jet and gamma plus jet production at 13 TeV. A comparison of the unfolded cross-sections of Z plus jet events as a function of ZPT with several predictions, theoretical predictions, is shown in the left plot. Here, data show good agreement with all predictions across almost the entire PT range. In the middle plot, we show the unfolded photon P2 distributions. Here we see that low PT boson part is described well, except leading order prediction normalized to the next to leading order. So the ratio plot, the ratio of differential cross sections for the two processes is also shown in the right plot here. The models including Sherpa and also next to leading order give Sherpa and MedGraph 5 EMC next to leading order give good description of the data for the ratio measurement. So uncertainty is basically dominated by modeling and statistic limited in the high PT region. In the same measurement, unfolded distributions for the angular separation between the Z and the closest jet also has been measured and compared with the different predictions. So in this measurements, all models are giving good predictions of the cross-section. And another important measurement at CMS is electroweak production of the boson in associated with with two jets at 13 TeV. In the study, the leading additional jet PT for boosted decision tree greater than 0.95 in the muon and electron channels, including the signal predictions from different from the PTI and Horvick plus parton showering histograms are shown. So in the right figure here, we look at the hadronic activity Vito efficiency for combined muon and electron channels as a function of the leading additional jet PT. Here data points clearly disfavor the background only predictions and are in reasonable agreement with the presence of the signal with Harvick plus parton shower predictions for gap activities above 20 GeV, while the signal with PTIA seems to generally overestimate the gap activity. Here is a summary. We can say that a large set of V plus jets measurements at 8 TeV and 13 TeV is presented. Differential distributions as functions of a broad range of kinematical observables are measured. State-of-art predictions are used for the data interpretation. Comparisons are made between the unfolded data and several theory at next to leading order predictions. Measurements provides a stringent test of our understanding of the standard model. There is much more ongoing, so stay tuned for the future results. Thank you.